We have talked about pKa, Ka, and their relationship a little bit so far in Unit 8, and we're going to look at that more closely in this section. So the protonation state, I think that's how you say that, I really don't know, of an acid or base refers to the relative concentrations of the acid and the conjugate base in solution. So this word that I'm having a hard time pronounce, the protonation state refers to, is the proton, the H plus, going to be with the acid, meaning it's going to be a weak acid, and it's going to be to the left or favoring the reactants, or is it going to be dissociated so that it's going to be away so that the conjugate base is present? Okay, that's what we're comparing. We're trying to figure that out. Where is the proton? Where is the H plus? Is it with the acid or with the conjugate base? Where is it? Okay, so it can be predicted, the state can be predicted by comparing the pH of a solution to the pKa of the acid in that solution. When the solution pH is less than the acid's pKa, then the acid form has a higher concentration than the base form. Okay, so this, I just wrote this down to help myself think about it. So when pH is less than pKa, then the acid concentration is higher than the base concentration. And that's because when you have a low pH, remember, that means it's a stronger, there's more acid present there than there is conjugate base. So that makes sense that the acid would be higher. Then the opposite is true too. So when the solution's pH is greater than the acid's pKa, then the base form has a higher concentration. So when the pH is greater than pKa, then the HA concentration is less than the conjugate base concentration. Okay, so this is useful in order, it kind of applies to acid-base indicators, which we have talked about briefly, and that's what this example pulls in. Okay, so a student pours a 10 milliliter sample of a solution containing acetic acid, which has a pKa of 4.8, and sodium acetate into a test tube. So the common ion is that acetate ion, the C2H3O2. The student adds a few drops of bromocresol green to the test tube and observes a yellow color, which indicates that the pH of the solution is less than 3.8. Based on the result, which of the following is true about the relative concentrations of the acid and the sodium acetate? So the sodium acetate there is representing our conjugate base, right? Because that's the common ion. The acetate part would be the conjugate base part. Okay, well, just reading all of this before I even look at the examples or the selection choices, right now we know that the pKa is 4.8, okay? When the indicator is added, it indicates that the pH is less than 3.8. So pH is less than 3.8. That is enough information for us to figure this out, okay? Because with that in mind, we know the pH is less than the 4.8, right? Because it's less than 3.8, which is even lower than that. So the pH is less than the pKa. So when, if you refer back, when it's less than, the pH is less than, then that means that the acid concentration is greater than the base form. Okay, so looking at our answer choices, A, acid greater than the other concentration, they're equal or they're less than, or it cannot be determined. Well, it can, we just did, right? So the acid concentration is larger because of the fact that the indicator told us the pH is very low. So that relationship there is just helpful for some background information. Okay, so when we are using or when we are doing titrations, we will sometimes use a pH meter, which we haven't done that yet, but we're going to. And so then when we plot the titration curve, we can get that we have the equivalence point and we have this vertical region and all the things that you get along the lines of a pH curve. Okay. Well, if you don't have the pH meter, then you can use an acid-base indicator. Now, the acid-base indicator marks the end point of the titration by changing colors, not the equivalence point. It is past the equivalence point, okay? So although we need the equivalence point for titration defined with stoichiometry, that helps us with all of our calculations in order to figure out pH values and all kinds of things about our acids and bases, that is not the same as the endpoint where the indicator will change colors. So you have to be very careful in your selection of your indicator so that your endpoint, when the color changes, is as close as possible to the actual equivalence point for your mixture, for your acid-base neutralization reaction, okay? So when acid-base indicators work, they are complex molecules that have acidic protons and they're weak acids, okay? So we just write HIN for the ion meaning indicator for these because they are so complex that we don't need to really worry about what their anion is, what that conjugate base is. We just know that this is how they work, okay? So they will exhibit one color when the proton is attached to the molecule as the weak acid form, and it will change to a different color when the proton is lost, when it's absent, when there is more of the conjugate base present. Phenolphthalein is one that we've used. We used it, it's that pink indicator that you wanted to get the baby pink. We had that competition in lab. So it's colorless in its acid form, and it is pink in its base form, which is how we used it. We added the indicator, the phenolphthalein, to vinegar. And so it started out as being colorless, no color whatsoever. And then as we added our base, it started to turn pink that way. And so that's just an example of how this indicator works. So when it's in acid form, it is one color. And when it is in base form, it's another color. So for some information about our indicators, I wrote on here rearranging the equilibrium expression. In case you don't know what that means, I guess I can write that down. Hopefully we are getting the hang of those by now. We've been doing them for a while, but so the Ka is equal to the H plus times the anion, the ion over the HIN. Okay, so that what I did was I just rearranged and I moved the hydrogen ion, the proton concentration, to the denominator. Okay, and the reason why this relationship is nice is because for most indicators, about 1/10 of the initial form must be converted to the other form before you can see a color change. So what that means is either 1/10 of the original, like let's say it started out as an acid, you have to use at least 1/10 converted to the base form in order for you to see a color change. Okay, so that is very helpful for us to predict when color changes will occur. And so what this 1/10 means is that the left side, or sorry, the right side of your equation here, this part, would equal 1/10. So we'll use that now in example 15. Bromthiamyl blue, which has a Ka value of 1 times 10 to the negative 7, is yellow in its acid form and blue in its base form. Suppose we put a few drops of this indicator in a strongly acidic solution. So it's going to be yellow to start, right? Because we're putting it in acidic solution. If the solution is then titrated with the sodium hydroxide, at what pH will the indicator color change first be visible? Well, remember, color change happens when it has at least 1/10 converted. So we will, in that rearranged form, we can say that the Ka over the H plus is going to be equal to 1/10, because whenever the 1/10 has been converted, then we'll be able to see it, right? So we know the Ka value, we can plug that in, is 1 times 10 to the negative 7. We don't know the H plus. We're going to solve for the H plus so that we can then get the pH at the end. And, over 1/10. So when you solve, you should get that the H plus concentration is 1 times 10 to the negative 6. Okay. So then now, when we have used up and converted at least 1/10 of our indicator, then we can say that the H plus is equal to this concentration. And when we take the negative log of that number, that gives us a pH of 6. All right, so that means that this will be the first visible change that we will see something other than yellow. Now, we have used, in Chemistry 1, we have used bromethymol blue before, and when it's in the neutral range, it starts to turn green. So this means, what my background information would tell me is that if it starts out acidic and starts out as yellow, when you get to a pH of 6, the blue is going to start to appear, but since it's a mixture of yellow and blue, to us, it's going to look green. Okay, until a further along point, then it will turn to just be blue when all of the acid form is gone. Okay, so these indicators, like I said before, there's lots of ranges for when they can change colors, and there's lots of indicators. So this table here kind of shows the pH range that's approximated for their color change, including what their colors will be. So like for the phenolphthalein, they don't have anything until about the 8 when it starts to change into pink, right? We just had the bromethymol blue, which they have the pH of 6 right there. What we just calculated is when we're going to start to see the yellow go away and start to turn to green before it's completely blue, when it's fully a base form. So these ranges are important for when you're going to choose what indicator you want to use with a titration, especially if you're not going to use a pH meter. So when you're choosing your indicator, you want to pick a titration indicator that will, the endpoint, when it starts to change color, will be as close as possible to your equivalence point. So with a strong acid, strong base titration, we know that it's a very, very steep section of the curve when you approach the equivalence point, because it's going to happen so fast and so drastic that it could happen with a change of a single drop. So many indicators can be suitable for this type. So they have in this graph pictured methyl red shows that it's going to change colors right before the equivalence point, and phenolphthalein would change right after the equivalence point. So those two would show color changes around the equivalence point, so they might be good options for a strong acid, strong base situation. And so usually when you're trying to pick your indicator, you pick indicators that with endpoints as far away as a pH of 5 and a pH of 9, which methyl red and phenolphthalein have those endpoint values. So you just have to pick something that changes within that range to be as close as possible to that equivalence point. Okay, so then with weak acid, strong base titrations, the vertical area around the equivalence point is a lot smaller. So we have to be more careful when we're picking the equivalence point marking point. So in this case, the methyl red would not be a good indicator because it's a lot farther away from the equivalence point than the phenolphthalein is. So you want to choose an indicator that has a midpoint as close to the pH as equivalence as possible with that. So we will have a lab where we actually study different indicators in different acidic solutions after the AP exam.